what we're going to be doing today is starting our last unit of PreCalculus. I can't believe it! Darker times are coming to an end. If you look at your calendar on the front of your unit, your new unit packet, you will realize quickly we are already behind, which is crazy because we just started today. How could we be behind? That's because we were supposed to start last week, but with our wild testing schedule and like everybody was in and out all different days last week, I didn't feel comfortable starting this last week when so many people were not going to hear it because of a variety of other tests they were taking. So we're starting today. I also heard, word on the street out there, is that many of you will not be here tomorrow either because of this thing called the STAR that you have to take, this silly thing called the STAR. Where are my juniors who are not going to be here tomorrow because of that? Quite a few. So if I'm right, it's only my AP Lit juniors who will be here, right? My other juniors are gone. All right, so also folks who didn't raise your hand, if you're with me tomorrow, they have moved our room again. I will look on the computer and figure out where so that you can go there and not have to go here. First period, I remember that one because it stood out to me. It's the gym. We're going to learn PreCalculus in the gym. Third period, I think we're actually in a classroom, but it might be on the other side of campus. So I will look it up in a minute and let you know. But there's a very, 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 very good chance that the unit exam that is scheduled for next Tuesday will not be happening. I have a call with some other PreCalculus teachers this afternoon where we're going to think through our calendar and decide as a cohort if it is feasible for us to take that exam next Tuesday. My gut instinct tells me it's not, but we will see what we can all come up with when we put all of our heads together. A lot of people, when I shared that in second period, began celebrating. Yes, small unit test, which I have to quickly follow up with. That is exciting if you don't want to take a unit exam, I know. It is not super exciting if you realize that maybe you bombed your unit exam last week, and then that's the only one that's going to be going on the A6 report card. So think about that before you celebrate. And I'm going to be thinking about that when I make decisions instructionally over the next week so that we're best supported in the classroom and in terms of our grade book. Question? I am. You're going to get detailed progress reports and some paperwork back in a few minutes, like toward the end of the period.
Jeanette said take-home exam.
Oh, take-home exam? Oh, yeah. I hate take-home. Because you know what you people do. Yeah. Hey, where can you take me to? Text. What's that? You may ask it Laura for sure. I love Barbie Sharpner. Yeah. I'll ask for you. Oh, look. Hurry. Oh, look, that was so thoughtful. I thought you needed your sharpener too. Problem solved. Okay, so today you will get paperwork back at the end of the period. The detailed progress reports that you are receiving back, the last grade on that is your unit exam. So you might want to go there first and look at how you did on that test. What I already did, so I don't have to answer this question a million times later, I have already taken that unit exam performance and gone back and replaced and adjusted everything up that I could based on your unit exam. For some of you, that was a lot of stuff. For others, it was not. It just depended on how your test went. Yep.
Are they on the grade book already?
Yes. All accurate in the grade book. It will be the same grade you get on your progress report from the school on Wednesday. Okay. Now that that's done, we need to start our last unit of the year. No. And it's one of my favorite units to teach. It's really fun. We get to introduce you to a new way of thinking about graphs and things like that, which is really cool. But what's sad and unfortunate is that what I would love to have like 10 to 12 days to teach you, I'm going to have to squeeze into 4 to 5 days. So you're going to get like the essential information, the non-negotiable. What does a pre-cal student need to leave pre-calculus knowing about polar curves and graphs? A lot of the cool stuff you probably will not get exposure to. And that makes me sad. If you're someone who is considering taking AP Calculus BC next year, this will have a direct impact on you because when we get to polar curves in calculus, there will be some stuff that you don't know that we'll have to fill in the midst of a BC curriculum. AB students, this has no impact on you. Polar curves are not assessed in an AB curriculum at all. And my seniors, it just kind of depends on what math course you end up taking next year, if this is going to impact you or not. The good news is, especially for my seniors, you will graduate having had exposure to polar curves. So when you get to college and someone mentions the polar thing, you're like, I remember this. My crazy teacher told me about this on a time. And on page 3, let me give you a second to flip to page 3 so you're at lesson 1 with me. There's a whole lot of text at the top of page 3, and I'm not going to read through that line by line. My original plan was like, each child will individually process the paragraphs, annotate, highlight, discuss their tables. We're not going to do that. Instead, I'm going to summarize in my fashion, like by telling you a story. Okay, are you ready? Blakely's story time. So she gets front row seat. Okay, so we all like superheroes in here? Batman and Superman. They're my faves.
Same.
Okay, so I'm going to tell a story. You just have to listen. I've always had a soft spot for Batman. Never really liked Superman. Batman was my jam, right? And I love Batman. When I was little, but then more recently, when they started like Dark Knight and all those movies, love Batman. I don't know if you remember Joshua Barrientos. Anybody? 2014.
Yeah.
He can do Bane. His voice better than Bane himself, and I made him say it. It's still recorded on my phone. I'll play it for y'all later, but it sounds like the movie. It's amazing. But I've always loved those movies, and until I started to think about Batman and Superman in more of a mathematical context. And you're going to giggle because you're like, who cares, right? But I'm going to convince you that I actually now am convinced Superman is better than Batman.
Yeah.
I know. And I'm going to convince you I'm going to We know. Okay, so I also have to sit when I tell stories, you know this. So I'm going to sit and get myself comfortable. Let's pretend for a second. Who can I pick on? Richard. Okay, you're going to be the star of my story, okay? Richard's out late at night, downtown Houston, right? Like, yes, driving like that. So he's out in downtown. He's actually not driving, he's walking the streets. Perhaps he just left what you people call the club late at night. And Richard is attempting to get to his car in downtown Houston when the worst thing happens and he's getting mugged. Right? Okay, this is my story, not your story. Richard's the star of the show, but it is my story. So he's getting mugged, held at gunpoint, give me your money, everything, right? And he's scared. I would be scared too. Giselle happens to also be walking by, and she sees Richard getting mugged. She pulls out her cell phone, and she's like, she's got Batman on speed dial, right? So she's like, Batman! Bat signal. Yes, she releases the bat signal, and she's like, hurry, hurry, hurry. Richard is in trouble, and he needs you.
How does she know his name?
And Batman is like, okay, tell me where he's at. And Giselle's like, okay, we're at the corner of Louisiana and Fannin. I'm making up streets right now. But
They're real.
I know, but I don't know if they actually mean it. This is where we're at, and Batman's like, okay, hold on. Let me put this in my GPS. Because what Batman has to do, think about this, is get in his Batmobile, right? And he has to, in the middle of the night, navigate the streets of downtown Houston, which you know is hard. Maybe Metro is interrupting and the one way, and he gets himself lost. Giselle is trying to communicate to him how to find Richard, but all Batman can do is get in his car and drive. Horizontally, vertically. I will stop and we will read if we cannot participate fully in my story. Can we, yeah? It's getting good. I know that it's good. So the tricky thing about Batman, is his car cool?
Yeah.
Yes,
Yeah.
awesome, right? It's like really, really cool car. But he's limited to his car, and he has to just drive down on the streets downtown. He can go north, south, east, west, and he will eventually get to Richard. But I'm worried, because he's not a Houstonian. He doesn't know our streets. He doesn't know how our drivers are. And so I'm a little concerned about Richard's safety because it's going to take him a little while to get there. Here's what's so cool about Superman. What can he do? Fly. He can fly. And so if Giselle's there and she's a little chicken, so she's not going out to save Richard herself. She's just on the phone making calls, right? And she's like, where's Batman? He's not here yet. Let me look up Superman, right? And so she calls Superman and she's like, okay, look, we've got a situation. Richard's in trouble. Can you get here? We're at the corner of Finn and Louisiana. He's here. And Superman's like, where's he at? Oh yeah, I'll be there so fast because I can fly. And all Superman needs, he doesn't need to get in his car, navigate the streets. He just needs to know exactly where Richard is. I'm pretending right now, day after our victory last night, that Superman's sitting on top of the Toyota Center having a party with Harden and all of them, celebrating the victory last night. And when his phone rings, he's like, yeah, what's up? Richard? Got it. Okay. Giselle tells him where he's at. Superman just stands up, rotates to where Richard is, right? He doesn't need streets, lefts, rights, anything like that. He just needs to rotate that direction and fly to Richard. And he's there, bad guy's done, Richard's saved, hallelujah. Batman's still stuck at a red 5 blocks over, can't get over to Richard. Yeah.
What about the Flash?
What about the what? I don't know who that is. I'm serious. I only know Batman and Superman, a little bit of Spider-Man.
I know, what about
I'm so sorry. Daniel, I feel like we just... Okay, here's what's so cool. Mathematically speaking, I think you kind of get my metaphor, right? Like, Batman limited to the streets, Superman can fly in the sky. Really a useful power, right? And if I think about this mathematically, what's true is that Batman is unfortunately limited to what we mathematicians call a Cartesian coordinate system. That's fancy, but that's what you've been learning all your life. Cartesian coordinates mean x, comma, y. Right? That's how Batman has to travel. He can go north, he can go south, left, right, maybe every once in a while a diagonal, but he's limited to like an XY kind of grid. Whereas Superman now, what you're going to learn about today, can actually fly in a polar coordinate system. With polar coordinates, let me summarize this real quick. Cartesian, ooh, this is pretty. What some mathematicians who are lazy call rectangular coordinates, that's x, comma, y. And in my analysis or example, Batman. Superman, polar coordinates. Check this out. We're going to shift everything now upside down on his head and communicate our location now, not as a horizontal and a vertical distance, but as a radius and a theta, an angle and a distance. And this is what Superman needs. All he needs for Giselle to say is, what angle is Richard at? Tell me how much rotation I need and how many miles is he away. I can get there in a flash. Flash.
So we're going back to using the unit circle?
We will be thinking about radian measurements. Not so much heavy in the actual circle, but we will need to be refamiliarizing ourselves with some of the ways we communicated angles before. Awesome. So that's what did it for me. Superman can now, like, he's my fave because he can just rotate, fly, save the day. Batman, I love that Batmobile, but, you know, he can only drive on the streets.
I mean,
So
he could fly too.
that's what someone else told me. He's got a cape where he can land
like
gently,
He's got like a
but he doesn't really fly.
He can jump off sometimes.
I don't know. We'd have to dig into that. What I want to do with you real quick is, okay, if you think about Cartesian stuff, remember when I say Cartesian, I'm talking about x's and y's. This definitely communicates someone's location to us, and I think you're really familiar with the fact that x could be positive or negative and y could be positive or negative. And that just tells me which way to move on my grid. Same with polar. I can have positive r, negative r, and I can have positive angles and negative angles. And so what I want to really quickly do is share with you what that does to our graph if one's positive versus negative, then actually get into some plotting of points. We're going to start very simple today by, like, if I relate this to Algebra 1, the days where you would just plot like 1, 5, negative 5, 4, plot points all over the place. We'll do that for a little bit. And then I'll show you the two simplest equations that can be graphed in polar. And eventually we'll start upping the bar quite a bit and getting into more of the intense analysis. But right now, I just want to share with you what it means to have a positive or a negative angle and radius. There are 4 basic scenarios that we could find ourselves in. This aligns hugely with what we studied back in our trigonometry units. If the theta is positive, we always start at 0 on our circle, right? Which way do we go if we have a positive angle rotation? Up is the nice way of saying it. Counterclockwise is the more technical description. Same is true here. Positive theta means a counterclockwise rotation. If you want to see that visually, that would mean starting here at the axis and going up and back. So negative theta, of course, would mean, I don't know, like clockwise? Or what some of you just visualize as starting at the axis and going down. Kind of make it more of a circle. So the R stands for radius, okay? What you can start to see just based on the paper that you picked up on your way into the room, these grids that we're going to be graphing on now do not have an x-axis and a y-axis. Instead, they're circles. They're actually called concentric circles. That means one inside the other, right, and building our way out. And there's angles that are labeled on the outside. The angle is really helpful. It tells us, if we're Superman, which way to face, right? And the R then tells me how many circles I should travel to. If R is 4, I'm going to hop out to the 4th circle, put a point. What this means, though, is R can be positive and can also be negative. If we have a positive R, we are going to travel toward theta. I will show you what that means in the context of a graph in a second. If the R is negative, that means we are going to be going away from theta. And I want to just show you how we would plot a couple of things to make sense of those last two annotations that we made on page 3. Bless. Bless. 3 in a row. Good work. All right. So let's go to page 4 and get some practice with graphs. All right, first of all, everybody mark off A because there's no point right there, so we can't do that one, unfortunately. And my lettering got all mixed up here, you can see, but I'm actually going to just go sideways, one row at a time. So I'm going to go over to B next, which is point E, unfortunately. So let me show you how this works. For whatever reason, whoever invented this mechanism for communicating points in polar started with the R and ended with the theta. To me, that's kind of backwards. It's more helpful when I'm looking at a point to find my angle of rotation first and then decide how far out I should move on that angle. So when I go to graph something like B, I hone in on the angle measurement first, 240 degrees. I'm going to choose to plot this point on the second circle because that's the one measured in degrees. If I give you something in radians, we'll plot it over there. I am still, just as if this were a trigonometric unit circle, going to start in the same place at 0. That's not changing. You already told me positive means go up, negative means go down. Still true. So this angle is positive 240, which means I'm going to begin my rotation up and go all the way until I hit the angle measurement of 240. Looks like it's down in quadrant 3, right? Just to keep my old lady brain straight, I'm going to put like a hyphenated line at 240 so that I can keep track of where Superman is facing, right? 240 degrees. Then, after I establish which direction it is that I'm at based on my angle rotation, that's the only time I go look at the radius. And this radius here is 2.5. So that means if I start at my center, I need to go toward my angle because the radius is positive. I'm going to head out on that line and I'm going to count circles. First circle is 1, second circle is 2, and I need 2.5. So I'm going to be right in between circle 2 and circle 3. I'm going to plot a point and call that, what is our name here? E. And there's our first shot at graphing the polar point. Yeah. I wish I'd zoomed in, right, so that we could see. I can zoom in up here, but unfortunately our graphs are all the same kind of tiny size. Actually, I'm not yet because I want to mix that. Let's go to the next row. This one's nice, it's in radians, and you'll notice the radius is negative here. We can talk about what implication that has when we switch the R to a negative value. I'm going to come to my radian polar circles over here. I'm going to rotate to 2 pi over 3, and because this is our first round of doing this, I'm going to go ahead and put this hyphenated line at 2 pi over 3 to anchor me in that angle. The tricky thing here is that once I establish the angle, the radius in this case is negative. According to our annotation earlier, that meant from the center, instead of going toward 2 pi over 3, I need to be going away, backwards then. Not heading toward 2 pi over 3, but going opposite. And I need to go back 1.5 circles. So there's 1, and a little baby half puts me right here for point B. I'll do one more together and then give you a chance to process this yourselves and see if we can agree on our pictures. This one's definitely, I think, the hardest one on the whole example. Let's see. Okay, always look at the angle first. Why is this angle scary? Negative and radiant, which is a little bit like a double whammy right there. For a lot of you, your graphical intuition deals with the negative just fine. You don't need to do anything other than like use symmetry to help you out here. If that negative weren't there, I'd go to my 0 line and I'd rotate all the way to 5 pi over 6. That's a positive rotation. I need a negative rotation. So it actually, based on the sweeping that I would do to get to the positive 5 pi over 6, if I mimic that same thing in a negative direction, I'm landing at 7 pi over 6. Is that okay with you guys? I wish I could animate this somehow, but I can't. What I usually do if it's a negative rotation is like next to the positive angle label here, I'll go right next to that and write like, oh, that just also could be written as a negative 5 pi over 6. Right? Mauro asked a question this morning. Will the positive and negative rotations always land in a place where the denominators are the same? Yes, absolutely. That's a helpful like clue to let you know if you're on the right track. You would not be going negative 5 pi over 6 and landing at like an over 4 location. We'll have to land at the over 6 location. Once I get here, I look at the radius. The radius is 4, so I count from the center, positive 4, 1, 2, 3, 4, and I label that F. What I'd like to do now is give you about 3 minutes to try and graph the remaining 4 points. We're going to put dots at all 4 of the additional angle and radii values, and we'll check it here in a second.
So the same thing how we did here where this was like positive and going down is like negative. So instead of going up, we're going to go down. Since 30 is 3, for the same distance from 30 to 30, so we go down since it's negative 30.
Alright, negative 33. 1, 2, 3. The answer will be right here. Can someone help me out with 2, 405? How do we have to do that, Abrielle? Can you talk us through it?
So you go past the 360 mark,
Yeah.
and then 360 plus 45 would be 405.
Okay, let me make sure everybody heard that, because that's definitely more my style, right? To give you an angle that's not labeled on the actual circle. So I want to make sure we say that again so that everybody hears that. Abrielle told me that when she saw the angle of 405, she went a full 360 and asked herself, how much more do I need to go to get to 405? It was 45 degrees. So she stopped there at 45 and then went 2 units out on her circle. We're calling that G. A student in my second period class said it just a little bit different. She told me, well, I just took 405 and subtracted 360. It got to 45, and that helped me land in that spot too. So I love that processing though. G, at any rate, over there in quadrant 1. Over here, pi over 2, and then negative 1 actually sends me down. So there's D right over there. And then a very interesting thing happens when I go to, what are you doing? What did he do? Liar. Something very interesting happens when I go to graph the last point. I start at 0, I rotate all the way to 225, but because the radius is negative, I go back 2 spaces, and it turns out G and H are in the exact same location. They are the same point. Not right next to each other, not like a little further away, exactly on top of each other.
So would we have to find all the different ways to get onto that?
Are you reading my mind? That's the next question. In pre-calculus, no, we're in pre-calculus. In trig, when we studied our unit circle, we talked about this idea before, that we can rotate different directions and land at the same location. There was a vocab word we talked about that defines this characteristic of points. No one has remembered it so far. There's a name for points that are equal to one another, like that. Oh, hold on, no, let me give you an example. 315 and negative 45. Can we agree they land in the same? Co-something. You're the closest I've gotten so far.
Convergent?
Coalition.
Coca-Cola.
Coefficient.
Cosine.
Cosine. These are co-terminals. That's because. No, you didn't. I would have heard you. That's because I can rotate different angles or take different radii values, positive or negative, and land in the exact same spot. So Abrielle read my mind. Are we going to have to find other ways to name points? Sure. Let's go to page 5 and see what you're going to have to do on a couple problems. I love you. All right. So let's take a peek here. First of all, I tried to zoom in a little bit closer. Do you all see the point T floating on that polar grid right there? It kind of blends in, but T is right over here. And we want to try to name that point in 4 ways. Basically, find 4 co-terminal points that would communicate to us the location of T. We are given a restriction. All of our angles need to stay between negative 360 and positive 360, which does limit me a little bit. Because for me, the easiest way to get to co-terminal angles is to just identify that as 135 and then add 360, add 360, add 360, add 360 4 times. But you can see that's going to really surpass the restrictions that they've given me. So I have to get a little bit more creative. I'll be nice and give you the first one. Okay? The first point that I think is very straightforward that we can all come up with, remembering, by the way, that our points have to come as r, comma, theta. The first one would definitely have an angle of 135, right? Can you all agree with that? And the circle that I'm landing on, I believe, if I'm counting, is the 4th one. So there's one way to represent that point, and probably the nicest way right there. Let's think about this, though. I need 3 others. If I'm answering this question, I need 3 other ways to represent that. 315 and then okay, I'm hearing the same thing from these two. 315 and negative 4 is my radius. Does that make sense? Let's see. I go from my 0 all the way 315. The reason 315 is so important, by the way, ladies and gentlemen, is because it's directly across from 135, symmetrical, right, in the opposite quadrant. And if I'm here, instead of going forward 4, I just need to take it backwards 4. So I love that. Oh, I don't know. I've got so many eager beaver volunteers today. This is beautiful. That's a new way to raise your hand. Go for it. I like that. That drew my attention.
3 pi over 4? Or 4 3 pi over 4?
4, comma, 3 pi over 4. I'm going to write that one over here. That's perfect. And it's expressing this one, right, in radians, which I love. We have to get on board with radians at some point very, very soon. Let's finish out degrees, too. I'm on the
Negative 4 and negative 45.
Nice. Let's take a look at this. Test him, see if this is right. He's saying negative 45 degrees. That's the first one where I haven't gone up. He's telling me go down 45 degrees. And you know where that lands me? 315. How nice. So I'll still go backwards 4 spots. Beautiful. There is one other one. Yeah, Julie.
Negative 225.
Negative 225 and 4. When I rotate negative 225, where does that land me? Right at 135 in a positive direction. 4 sends me out. Basically, what I'm looking at when I address a question like this is that if I start, I'm always starting here at 0, right? I want to ask myself, what 2 positive angles should I take that will line me up with a positive radius or a negative radius at that point? And then what 2 negative rotations do I need to take that line me up either exactly where I want to be or exactly across from where I want to be? It's always going to be either where we're at or the exact opposite location, okay? Just for consistency's sake, wouldn't it be great to convert all of these to radians real quick? Even though the problem came in degrees, nothing wrong with that. This would be negative 4, 315, 7 pi over 4. This would be negative 4 comma negative pi over 4. And this one 4 negative, that's not an eraser, that's a phone, 5 pi over 4. And I've got equivalent angles for all of them. Like I said, there are 2 problems from your homework, I think, that ask you to do that. Real quick while I'm thinking about your homework, let me make sure I directly express this to you guys, because I didn't say this in my other classes. You all picked up this piece of paper, right? It's not just for fun for you to scribble over. This is where your homework is going to be done, because your homework asks you to plot points and to graph things. So what I want, and listen carefully, you'll forget this later, 1 through 4 should all live on the first graph right here, because you're just putting 4 dots on there, 1 through 4. 5 and 6 have to happen not on a graph. I prefer they happen on the back, like you just do the work in 5 and 6 on the first piece on the back. And then 8 through 11 should all happen on the second circle. Okay, so it's going to kind of jump into, trying to say it again.
Wait, on the back?
But on Wednesday, when everybody turns that in, I don't want your own pieces of paper or anything like that. I want my circles right back, because that's where all of your work will be. All right, and there's one additional new piece of information that I need to share with you. There are 2 checks for understandings right here. We're not going to worry about those because they're very similar to what we just did, and you'll get practice this evening. But there are 2 additional skills that everyone in my previous classes seemed to take a liking to, way more than these plotting of points. So let me remind us all real quick, because there's definitely some big idea stuff that we're addressing today too. It's exciting. This is the first time you've ever heard about the fact that there's something other than a Cartesian coordinate system. There's another way to graph besides an x and a y axis. As a reminder, up until today, you always graphed things in a Cartesian plane. That meant you plotted points of the form x comma y. Today, you're finally being introduced to what's called a polar coordinate system, where our points come as r comma theta, okay? In the Cartesian coordinate system, like old school stuff, there are actually 2 kinds of graphs that we could visualize that mathematicians call basic graphs in a Cartesian plane. Basic meaning something different than I think the way you people use that word out there in the streets. The 2 basic graphs in Cartesian coordinates are y equals some number, like y equals 2 or something like that, and x equals a number. These are basic because they're pretty elementary lines, right? Just straight up horizontal or straight up vertical. There are also basic graphs in the polar coordinate system, but they are not horizontal and vertical lines. So what I want to show you is what these ones look like over here, because that's the last chunk of your assignment. You can probably anticipate if the basics in Cartesian were x equals and y equals, the basics in polar are going to be r equals and theta equals. We just need to talk about what that looks like on a graph, and we'll get to that on page 6. All right, so let's do this. Our first polar equation. We will definitely see some more complicated ones very soon. They're actually beautiful. Some of you have seen some of these curves like on the internet every once in a while, like they're called roses. They look like they're flowers. Those are polar curves. Some of them cardioids. They kind of look like the organ of the heart. There's all kinds of really pretty things that we can look at, which we'll get to later in the week. For now, the basics. R equals 2 is about as basic a polar graph as I could imagine. This is telling me my radius is 2. I'm coming down to my graph then and making sure I'm internalizing that it makes absolutely no difference what the angle is. I could be rotated here, 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 anywhere around, but my radius needs to be 2. What shape do you envision we're going to be drawing here for this basic polar graph? A circle. actually a circle just tracing the second ring of our polar grid. If I go out 1, that would be r equals 1. I want to go out 2 because I have r equals 2. I, of course, can't draw circles, so I just overcompensate by going over it again. So one family of basic polar graphs are circles. The only other exposure you've had to graphing a circle was back in conic sections when we talked about parabolas, hyperbolas, ellipses, and circles. As a reminder, a circle came of the form x minus h squared plus y minus k squared over that r squared, and it had to equal 1. We knew we were looking at a circle if we had maybe like x minus 4 squared over 16 plus y plus 1 squared over 16 equals 1. How do I know this was a circle? Matching. That told me go up 4, go down 4, go left 4, go right 4. And I saw my beautiful circle. And that wasn't difficult back then. Y'all actually got really good at eyeballing like, oh hey, that's a circle. But now, I can graph circles just like this. How nice is that? So much easier. And you've just never known that before because we hadn't studied polar yet. Flip side, what if theta equals a number, like pi over 6? That means, doesn't matter what the radius is. Could be really small, could be really big. My angle is pi over 6 for all radii. What is this graph going to look like? A line. Exactly. Here's pi over 6. Some students stop at the center. That's not true. Radius could be anything, positives and negatives. So that line has to extend all the way. I can't draw straight, but you get me, right? All the way through your polar grid. And another basic graph right there. Like I said, there is opportunity for you in your homework to get practice with the basic graphs before we up the rigor and attempt to graph much more complex curves and polars. Okay, so right now, listen before you start doing things, because y'all shuffling of crap starts to irritate me when I'm trying. Okay, I'm going to give you paperwork back. Here's what needs to not happen. Miss, can I? Miss, when's this? Miss, I want to. Stop it right now. I had some really salty people in second period who were very upset with me because I'm not letting them do correct and put anything. But, Miss, I'm sorry. I am. I know y'all are stressed. I'm stressed too. And at this point, limits, we've got to close the book on that. We are starting polar fresh today. If you want to improve your grade, you should prioritize the future assignments that you have on polar, because that will have a very significant impact on your grade if you take it seriously and you do well. And our polar stuff, I'd be more than happy to give you an opportunity to do corrections on that because it's relevant and it's in the moment and it's what we're learning right now. What I don't need is you stressing out about limits and derivatives when that ship has sailed and that test has been taken. Your final reassessment opportunity on limits was your unit exam. So when you get your detailed progress reports, a lot of you, I said this already, will notice some of that stuff you never turned in is magically an 88 now. That's because you got an 88 on your test and I went back and replaced everything. So no, like, Miss, can I? No. You're going to get a lot of paperwork back, file it away, put it up, internalize your grades, and let's move forward together. Deal? Okay, I'll probably need help because there's a bunch of stuff, so I will volunteer some of you as we're talking. Bye! See you later.